Let's dive right into one of the most intense, high-stakes debates in modern physics. Welcome to this explainer, where we're unpacking a profound cosmic mystery that has brilliant scientists totally divided. And honestly, it might just break everything we thought we knew about the universe.
So, is the universe filled with invisible dark matter, or is our fundamental math of gravity simply wrong? That's the ultimate question we're exploring today. We're going to act as impartial referees in this massive scientific clash, because right now, the very math holding the cosmos together is being put to the ultimate test.
Here's our roadmap for today. We're looking at the missing mass mystery, galaxies and the JWST, colliding galaxy clusters, the external field effect, wide binary star tests, and finally asking if we are in the middle of an unfolding scientific revolution.
Part 1. The missing mass mystery. The reigning champ versus the challenger.
For decades, astrophysics has had a huge problem. You see, galaxies rotate way too fast for the amount of visible matter they actually contain. By all rights, they should literally fly apart, but they don't. So to solve this, we've got two contenders. In one corner, the reigning champion, standard cosmology, which says invisible, non-baryonic dark matter provides that extra gravitational glue. And in the other corner, the scrappy underdog, modified Newtonian Dynamics, or MOND, which proposes that we don't need dark matter at all if we just tweak the fundamental laws of gravity at very low accelerations.
And MOND is a remarkably stubborn challenger. Introduced back in 1983, it uses a universal acceleration scale to accurately predict how flat galaxy rotation curves should look, all without inventing any invisible particles. While dark matter models often require custom-fitting an invisible halo to every single galaxy just to make the math work out, MOND yields these tightly constrained predictions that hit the nail on the head almost every time. It even successfully anticipated the baryonic-Tully-Fisher relation.
Part 2. Galaxies and the JWST, the early universe problem.
Let's zoom out to the very edge of the observable universe. The James Webb Space Telescope has honestly thrown a massive wrench into standard dark matter cosmology. In the 80s, the standard model predicted a really slow, hierarchical process for galaxy formation. But JWST is finding these huge, fully mature galaxies existing far earlier in cosmic history than dark matter models said was possible. The kicker? Back in the 90s, MOND actually anticipated this rapid early formation of massive galaxies. The scientific community is deeply divided over this right now. Just listen to this quote from the source material. But in the early universe, dark matter models are turning out to be abject failures. The community seems to be in the usual process of gaslighting itself into denial. That really shows you just how intense the friction is right now between observers and theorists.
Moving on to Part 3. Colliding galaxy clusters, the cosmic wrecking yard.
Now, let's zoom in a bit from the early universe and look at massive colliding galaxy clusters. These are the largest gravitational events in the cosmos. When they smash together, do these collisions disprove MOND, or do they disprove dark matter? You'd think they'd provide a clear winner, but the evidence actually gets incredibly messy.
Yeah, both theories have glaring weak spots here. Dark matter struggles to explain the immense collision speeds of clusters like El Gordo. That one exceeded 2,500 kilometers per second, which is ruled out at 6.2 sigma in standard models. Statistically, it shouldn't exist. On the flip side, MOND famously fails to explain the missing mass in the core of the bullet cluster. To make their math work, MOND advocates have to rely on ad hoc solutions, like suggesting the cluster is filled with undetected particles, like sterile neutrinos.
Part 4. The external field effect, the gravitational background.
To understand our next battleground, we have to grasp a really unique feature of MOND, known as the external field effect, or EFE. Think of it like trying to measure the tiny gravitational pull of an apple, but you have to ignore the massive pull of the Earth you're standing on. In MOND, the background gravitational pull of a massive external system, like our Milky Way galaxy, actually overrides and suppresses the modified gravity effects within a smaller internal system, like our solar system. Basically, the background noise washes out the signal.
So, this begs the question, how do we actually test MOND without that background interference? The crucial point is finding a system with low acceleration that is isolated enough to avoid this external field effect. Which brings us to Part 5, wide binary star tests, the microscale showdown. This search for an isolated system brings us all the way down to our local stellar neighborhood to look at wide binaries. These are pairs of stars orbiting each other at vast distances.
At these incredible distances, the gravitational pull between them is incredibly weak, which perfectly isolates the MOND acceleration scale. And because they're right in our cosmic backyard, any weird gravity we find can't just be blamed on dark matter, because there just isn't enough of it locally to affect them.
But here is where the drama really peaks. We have this massive binary dispute. One group of scientists analyzes high-precision data and finds a massive MOND gravity boost. But then a rival group looks at the exact same data and finds absolutely zero boost, perfectly aligning with Newtonian gravity. How do two teams look at the same data and get totally opposite results?
Well, the results completely diverge based on the statistical math. It changes entirely depending on whether your baseline model treats the 3D orbital size of the stars as an independent parameter, or if it uses a geometric model to derive that 3D size from a flat 2D view on the sky. The supposed anomaly is incredibly sensitive to the exact mathematical recipe being used.
So the discrepancy isn't about the telescope data being wrong. It's a fierce debate over a methodological minefield. We're talking about assuming versus calculating the semi-major axis. It's about how strictly you filter out noise from hidden, unresolved third stars that might be lurking in the binary system. It comes down to differences in Bayesian sampling algorithms and how you apply proper data quality controls without accidentally baking your own bias into the results.
Recent comprehensive reviews suggest that when you apply the absolute strictest quality controls and properly account for those hidden third stars, the MOND-like signal vanishes. The anomaly is incredibly sensitive to statistical modeling, meaning the claimed proof from modified gravity here might actually just be an artifact of how the math was done.
Part 6. An unfolding scientific revolution, the future of gravity. So where does this sprawling, cosmic showdown actually leave us today? Some astrophysicists firmly believe we're standing on the precipice of a massive shift. To quote the sources, we need to develop a new, realistic cosmological model. We are talking about a paradigm shift that happens in science only once every 100 to 200 years.
Let's look at the current state of the showdown. Dark matter reigns supreme on large cosmic scales, but fails to predict early JWST galaxies and struggles with extreme cluster collision velocities. MOND brilliantly predicts galaxy rotation, but struggles with cluster cores and relies on highly sensitive statistical models for those binary star proofs. Both sides have massive victories and glaring weak spots. Looking to the future, this tension is actually birthing entirely new theories, like superfluid dark matter, which attempts to blend the absolute best of both worlds.
I'll leave you with this question to ponder. Are we on the verge of a new paradigm in physics, or does dark matter just need better simulations to explain what we are seeing? As we build better telescopes and run tighter models, are we about to realize that our fundamental mathematical understanding of the universe has been broken this whole time? Or is the dark universe simply more complex than we ever dared to imagine?